Hello, welcome to lesson 16. In this lesson, we are going to explain some of the effects of refraction. We shall also look at the apparent size of a fish situated in water, and last we shall look at total internal reflection and critical angle. Let's begin by explaining some of the effects of refraction, and we are going to explain why the sun is seen shortly after sunset. So this is the illustration. When the sun is below the horizon, then it has set. But to an observer, at this point, we can still see that sun even after sunset or shortly after sunset. Why? It is because of refraction. Now, when we talk of the horizon, we are meaning a horizontal line drawn on the surface of the earth. So this is the horizon for this observer at O. Now, we also need to note that in the evening, the layers of air just above the earth is cooler as compared to the layers of air far above the earth. And also we need to note that because of that, the layers of air just above the earth is always more dense as compared to the layers of air far above the earth. And we also need to know that when the light rays are moving from a less dense medium to a more dense medium, it refracts towards the normal. But if it is moving from a more dense to a less dense medium, it refracts away from the normal. So in this case, it is moving from a more dense to, it is moving from a less dense to a more dense medium. So because of that, there's going to be refraction towards the normal. So the light rays from the sun is going to undergo continuous refraction towards the normal. And then to an observer at O, the light rays will be appearing to be coming from S1. And so the apparent position of the sun is going to be at S1. Therefore, the sun is going to be seen shortly after sunset. A similar situation also occurs in the morning during sunrise. The only difference is that in the morning, the layers of air just above the earth is warmer as compared to the layers of air far above the earth. Let us also explain why a stick partially immersed in water appears bent. So this is the stick. So light rays from the tip, the lower tip of the stick, undergoes refraction away from the normal, because we are moving from a more dense to a less dense. And then to an observer here, the tip appears to be slightly above the actual position of the tip. Hence, it will appear to be bent. Hence, that stick will appear to be bent. Let us also explain this one, why the pond appears shallower than it really is. Same scenario, light rays from the bottom of the pond will move to the surface, and at the water air surface, it is going to undergo refraction still away from the normal. It's going to undergo refraction away from the normal, and to an observer, that the light rays will be appearing to be coming from a position slightly above the real position of the bottom. So the bottom will appear to be at a higher position, slightly at a higher position as it really is. So because of that, the bottom of the pond will be above here, and the pond will appear to be shallower. Let us also explain this. You're saying that we're going to look at the apparent size of a fish situated in water. Now we need to note that a fish situated in water usually appears to be bigger than actually it really is, and that is simply because of refraction. Now we need to note that many times we think that, we always think that the surface of the water is flat, completely flat, but that's not the case. The surface of the water always has countless ripples, and because of that, it appears to be concave. appears to be concave, just like we are seeing here, because of the countless ripples. And so if we have this fish, if we draw a ray from the head of that fish, and that ray is going to move to this boundary of the water and air, and it will undergo refraction. It will undergo refraction away from the normal, and then it will appear to be coming from there. So this will be the apparent position of the fish, of the head of the fish. And also a ray from the tail will undergo refraction at the water air boundary and will appear to be coming from this side, and that is going to be the apparent position of the tail. So in other words, this water is going to be like a convex lens, and then the fish will appear to be bigger than actually it really is. That will only occur mainly when the fish is at the focal length, so it is at the focal point of this lens, of the lens of this, because we are saying that this water surface is going to be like a convex lens. The water surface is going to be like a convex lens, and so if the fish is situated at the focal point, that means that it will appear to be bigger than it really is, or it will be appearing to be magnified if it is situated at the focal point. Let us also look at total internal reflection and critical angle. Total internal reflection is a reflection which occurs when light rays reflect within the same medium. This is when reflection occurs within the same medium, and we are going to see that. So we are saying total internal reflection of light rays is a reflection within the dense medium when the angle of incidence exceeds the critical angle. That's the definition. Now we are going to explain how that occurs. Let's explain that, and then also shall explain the critical angle. Now we need to note that when light rays is moving from a more dense to a less dense medium, it refracts away from the normal. So light rays incident from a more dense to a less dense medium is going to undergo partial refraction and partial reflection. So some of the light is going to be refracted and some of the light is going to be reflected, but more of the light is going to be refracted. Now so this is what we shall have. So the light rays from, for example, from glass to air is going to undergo partial reflection and partial refraction, but more of the light is going to be refracted. More of the light is going to be refracted. So when we increase this angle of incidence I, remember we are moving from a more dense medium to a less dense medium. This refraction is going to occur away from the normal, and so it's going to reach a certain point when the angle of refraction is going to be 90 degrees. It's going to reach a certain point when the angle of refraction is going to be 90 degrees, and at that point the angle of incidence is going to be called the critical angle. When the angle of refraction is 90 degrees, the angle of incidence is going to be called the critical angle. But still, we shall have this partial reflection. Now, when we further increase the angle of incidence, all the light rays will undergo reflection within that denser medium, and that is going to be called total internal reflection. And that's what is going to happen. When we further increase the angle of incidence beyond the critical angle, all the light rays is going to undergo reflection, and that's going to be called total internal reflection. Let us define critical angle. which is represented using the letter C. The critical angle is the angle of incidence whose corresponding angle of refraction is 90 degrees for a ray moving from a more dense medium to a less dense medium. A more optically dense medium to a less optically dense medium. Let's also look at the conditions for total internal reflection to occur. 1. The light rays must be moving from a more dense medium to a less dense medium. The light rays must be moving from a more dense medium to a less dense medium. Then also, we need to note that the angle of incidence must be greater than the critical angle. So, thank you for your attention. In the next lesson, we are going to look at the applications of total internal reflection.